good evening, everyone. Welcome to this problem solving session. So, we are in this week 5. So, if you have any doubt related to the previous session, then you can ask, or we will start. So, let me summarize this week content. So, what was covered in this week lectures was uh, forward and reverse bias junction. So earlier in the previous sessions, we have seen like how the junction band diagram looks like when you are when you are when you operate in equilibrium. So we drawn equilibrium band diagram, but this week we will see like how does the band diagram and those and the current and drift and diffusion current looks like in in with applied bias. Basically, this is the non-equilibrium scenario. So and then so basically what happens when you apply a bias, then like this minority carrier injection happens, and like then this diffusion and drift current flows in the diagram. Then next, it was the current in the current equation in reverse bias and forward bias, and how the depletion and capacitance and forms in p-n junction. So basically, what happens is, let's say you did not apply a bias, then you can draw a equilibrium band diagram. So the equilibrium band diagram quickly you can draw just like this. So you draw EF as a flat, and if this is your junction, and this side is it's this side is n type, and this side is p type. So away from the junction, your away from the junction, your band will behave like your junction. This is basically neutral or quasi-neutral region, neutral or quasi-neutral region. So in this region, basically the semiconductor will have its like original, suppose, without having any junction consideration property. So what are those properties? The 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 conduction band will lie closer to the Fermi level. So this here will be the EC, and similarly in P side in the bulk region, the conduction band will be closer to the EV. So now in this transition region, basically, so now you can draw uh, draw here the conduction band here, and similarly you can draw valence band here. And then you can draw you can join this curve, and in the this neutral region it will band like this, and uh, it will form like this. So this is the like quick. This is the quick quick way of just wait. Just hello, hello. Yeah. So This is the quick way of hello. Yeah, this is the quick way of drawing the band diagram. So you can draw even other levels just like this, and this just let me draw it with very honest. Yeah. So this is like this you can draw. So this is the equilibrium band diagram. So now what happens is now this there are certain electrons are there in this band, free electrons are there, and similarly these holes are there in this band, and which feel barriers. So now this, for the electrons this barrier is there, and for holes this barrier is there, so they can't cross. So ideally in the equilibrium, whatever the barrier cross this there is correspondingly like equal number of electrons cross their barrier. So net current in this is zero. Now when you apply a positive re- uh, positive bias, then what will happen is the Fermi level in this n side. So basically, the suppose this is the PN junction. So this is P side, this is N side, and you apply a bias. You apply a bias, and you are applying a positive voltage in this direction, like, and let's say this is at the zero potential. So now what will happen is the this like the barrier in this will be reduced, because you so now you can say that the chemical potential of or Fermi level difference of this level is reduced, and you can draw the band diagram like this. So this barrier, so one side if you assume this, and then other side it will be like this. The conduction well will move up, and so is the Fermi level. So this is approximate picture, because the band diagram we draw is in under equilibrium, but this is now the Cauchy Fermi level actually. So now since this band moves up, this electron has this barrier, like this barrier is reduced, so the electrons can jump from here and holes can jump from there. So that's why uh, there is a flow of current. And if you take the apply bias in other direction, so this barrier will become down, and this barrier become more. So now if you like the now the current will get reduced, because like these electrons in this side feel more barrier compared to this hole in this side. So that is like quick summary of what happens in the PN junction in when you apply a bias, what happens to the PN junction. So now what happens is uh, when you apply a bias, so not all the electrons. So basically, these electrons are going into the positive p side, and basically you can consider this as a minority carrier injection. So these electrons are minority charges in the p region, and if you make an approximation, then you the this tail is small, and like the whatever the n type of carrier whatever injected into this direction into the p region uh, is the concentration is much smaller compared to the concentration of uh, concentration of majority carrier in the p region. So now, like if you apply a bias, So what will happen, like when you don't apply a bias, so what happened is, uh, now if you apply a bias, so let's say this is the uh, uh, let's draw the concentration of the carrier. So let's say this is 0 and this y-axis is at log scale, y-axis log scale. So now if you assume this is the junction and this is p side depletion region and this is n side depletion region. So what will happen is, so under equilibrium, what is the concentration of, uh, so this is concentration of electrons in p n p naught. So this is the concentration of electrons under equilibrium in p region. Similarly, you can find this is p n naught. So concentration of holes, concentration of holes in n region. Similarly, you can draw, you can this is so linear scale you can't draw because now if you draw majority charge carrier concentration, so that will lie here, and that is p naught. And similarly, you can write, if your concentration in both side is same, then you can write here as a uh, p n naught. So let me just draw this as a bit dashed line, so that yeah, this is dashed line. So now what happens is, under equilibrium. So under equilibrium. So what has happened? Like some of this carrier will get diffused, and those carrier will inject here, and as you go as the carrier injected here, this recombination will take place. So this so after some time this kind of profile will make. So after certain distance, the all the carrier will get recombined, and your concentration will become equals to the minority carrier equilibrium minority carrier concentration. Similarly, it's in this direction also. So this is delta p at zero bias. So this is also delta n at zero bias. So now when you apply, and if you assume the so if you assume that uh, the if you assume that uh, if you assume there is no generation recombination in the depletion region, then you can take this concentration is flat in this region. So you can draw by this, and then you can join this curve by this, and you can get approximately this current. So this current you can draw. Now what happens is, you apply a bias. So basically, like as you apply a bias, so because now the barrier is reduced and more carrier will get injected. So this is delta p at x equals to 0 at uh, something v forward bias. And similarly here delta p at x equals to xn at some delta v forward. So this much concentration difference is there, and because of that the current will flow. Similarly, in the reverse direction, this concentration become lower, and this will become like the carrier will swept out away from this junction, and you can draw the current equation from that, just by taking these two currents and just adding up this delta p and not and this current due to this concentration or diffusion current. So then you can get the current equation with this. So yeah, you can get the current in this direction. The current will you will get the current equation from here. So yeah, so this was this minority carrier injection in this, and basically you can from this slope. So basically this profile of this you can get the current in the in the junction. So now, if you now let's just move to uh, the capacitance and see like here, because this depletion region is there, and that is devoid of any kind of charge carriers, and there this you can assume like a dielectric region or region without any charge carrier, and there is a charge in this direction if you apply a volt. So that if you calculate the depletion bit total W, then you can calculate the capacitance capacitance uh, just as C depletion capacitance as epsilon naught A by WD. Basically, WD is the depletion rate, and which is proportional to uh, I think it's uh, Q just uh, so yeah, 2 epsilon by Q ND. This epsilon by ND, 1 upon ND plus 1 upon NA times V built-in voltage plus the applied bias. So that you can get, and basically the depletion bit is directly proportional to square root of VBI plus V applied bias. So VBI minus. So basically, if you applied a and you can take a mode, and basically if you apply a negative uh, in reverse bias we applied as negative, and in forward bias reverse this is positive. So basically you can calculate the depletion rate based on this equation, and like if you can calculate the deflation bit with basic Gauss law and those equations, and that also you will reach the same conclusion or same answer you will find. So if there is any doubt up to here, you can ask. I will pause for some time, and then if there is no doubt, then I will just uh, solve this last year uh, uh, problems based on the content whatever presented in today's this week's session. So uh, first question is talks about For a forward bias PN junction given below, choose the associated Venn diagram for a from the given option. So the forward bias junction. So basically, your barrier will become less, and then you can how and then the Fermi level will be like you need to draw the quasi Fermi level because now the like the junction is not under equilibrium. So then you can this as we see like since this positive bias is applied at the positive side, so this is forward bias, and then like based on these options, let's just figure out which diagram. So so this in this diagram, EFN and EFP are same. So this is the band diagram under equilibrium, but since we applied a bias, and that is the case of non-equilibrium case. So in this applied bias case, your Fermi level can't be flat. So this is wrong. Uh, Similarly, this one is also wrong, and also this is drawn in incorrect way. So this band gap should be same, and this this is also drawn wrong. So this like one side you should not have other barrier compared to electron for other side. So this is also wrong actually. So if you consider a similar type like homo junction, like uh, if this is silicon and this is silicon, then this band diagram is wrong because for homo junction, actually band gap should be same. So in this, the band gap in this direction is different compared to the band gap in this. And yeah, so the like it's not given any thing about the material characteristics, so it can be heterojunction also. So this option is wrong because here this Fermi level is given as flat, so that's why it's wrong. And in the PN junction and this so the in this case the p side barrier become lower compared to the n side barrier, but it's not like that. So this barrier, it's not reduced like even if you apply any voltage, this barrier does not go even at zero. So it is reduced like quite a like it's not reduced like even near zero going is increase like the current increase very high, because that is in like the delta n is exponential relation with v applied bias. So what has happened, if you apply if you change bias very small, then also you will say see a large change in minority carrier injection current. So in this like when even when you apply a large forward positive bias case, this the voltage applied across the junction is voltage dropped across the junction is very small. It's very few order of very few fraction of your built-in potential. So and then the question asks like where that other voltage drops. So basically this other neutral or quasi neutral region has a resistance. So some voltage dropped across that region, and also it has a contact resistance. So the other the voltage dropped across the contact region also. So this, even if you apply any bias, any larger bias, this can't be the case. So if your band diagram in equilibrium is looking like this, then it just can't like the conduction band, it can't go like this actually. So the correct answer based on these choices will be the B one. Yeah, so if you have any question, you can ask about this problem. So I will pause for some time. Yeah. Yes. Okay, so let's move to next problem. So in a forward bias PN junction, the correct option is the barrier across the junction reduces proportional to the applied bias, resulting in the drift of the majority carrier across the barrier. No, no, this is not the drift; it's the diffusion. So a diffusion of minority carrier. So the barrier across the junction increases proportional to this is wrong. Barrier reduces in forward bias, resulting in the drift of majority carriers. This is wrong. The barrier across the junction reduces proportional to the applied bias, resulting the diffusion of majority carrier across the barrier. So this is also uh, uh, this resulting diffusion of the this the yeah. So the barrier across this junction will reduce uh, so and so the correct answer will be the diffusion of the minority carrier. Actually, this is wrong option. The barrier across the junction reduces proportional to the applied bias, resulting the diffusion of the minority carrier across the barrier. So basically, here here what happens is your minority carrier will get diffused in this region, and similarly, this the hole in this region diffuse in this region n side, and the electron in reduce in this side. So that is so yeah. So that is the correct answer will be the this one, not this one. So the barrier across the junction increase proportional to the applied bias, and this is wrong actually. The resulting distribution of majority carrier uh, across the barrier. This is also wrong. So the correct answer is D. Okay. So let's move to next problem. The figure below shows a carrier profile across a PN junction. Uh, the impurity doping concentration ND is 2 power 15. So this side it's 2 into 10 power 15 per centimeter cube, and this side 8 into 10 to the power 15 per centimeter cube. So, and the voltage VA is applied across the junction. Based on the given data, answer the following question. So, uh, so the we need to tell diode in which region of operation it is. So, as you can see, like the concentration of holes at x equals to at n side boundary, n side depletion region boundary is increasing actually. So in the equilibrium case is P and naught, but it is increasing with the bias, and here also it is increasing with the bias. So like that case as we discussed is happens in the forward bias. So in the forward bias, so the biasing operation is the forward bias. S there is an excess minority carrier available at the age of depletion region. Yeah, so this is the correct answer. And equilibrium condition as there is no movement. So this is wrong because this profile gradient is there. There should be a diffusion of these minority carrier injected minority carriers uh, will be there. Similarly, diffusion here and corresponding drift of majority charge carrier will be there. Uh, Other option is reverse bias. This is wrong. As there are excess minority carrier available in the quasi-neutral region, this is wrong explanation. Forward bias as the excess majority carrier available at the edge of diffusion. There is always excess majority carriers are available at the edge of the depletion region. So this is also the incorrect option. Reverse bias as there are negligible minority carrier available at the edge of depletion. No, this is wrong because there is excess of this minority carrier here and minority carrier electron here, which is minority carrier in p side, and similarly holes here, which is minority carrier is n side. So this is also wrong option. Equilibrium condition as the carrier concentration are considered constant at any given position in quasi-neutral region. So no, the uh, quasi-neutral region, like always until unless you consider that short short diode approximation if you make, then other than if you make long base diode approximation, then quasi-neutral region always have the equilibrium carrier concentration. So this in the long base case diode where this length of P and N region is large compared to the diffusion length, then you can consider that as a long base diode. And in the long base diode, like you can assume there is there is equilibrium concentration equilibrium carrier concentration prevails condition prevails. So here in the long base diode where L is much larger compared to the diffusion length, so diffusion length there is this is diffusion of holes in n region. Similarly, here L is much larger than comparison diffusion of N in diffusion of electrons in the p side ring. So this is the this question. If you have any doubt, then I will pause for some time. If you can ask some question if you have doubt. Hello, any doubt? Sorry. Hello. Okay. If you can like have any doubt, then you can raise your hand or type in the chat box. Uh, Next problem, it is asked the steady state minority carrier concentration in steady state minority carrier concentration in P side and N side is respective. So basically in the quasi-neutral region, the steady state minority carrier concentration P N naught or NP naught is basically given as by the law of mass action. So this is Ni square by Na. Ni uh, this is Ni square by Nd, and similarly this side is Ni square by Na. So that you can calculate, and that this Ni square is 10 power 10 whole square divided by P n naught it is, and this is Nd, and which is Nd is given at 2 to the power 2 in, so this is 10 power 20 divided by 2 into 10 power 15, and which will become 5 into 10 power 4 per centimeter cube. Similarly, Np naught is 10 power 20 divided by Na, and A is given as 8 into 10 power 15, 8 into 10 power 15, and which you can write as 10 into 10, 10 power 4 divided by 8, and that you can write 1.25 into 10 power 4 per centimeter cube. So the correct answer is uh, the correct answer is 1.25 into 10 power 4 and 5 into 10 power 4. So the B is correct answer. This was fairly straightforward question, just formula substitution. So the minority carrier concentration at the edge of depletion region with the applied bias with an applied bias of VA equals to this is, so basically this you can calculate. So n of minus xp is uh, np naught times exponential of qva by kbt, and that if you put, so np naught you calculated, so it is uh, 1.25 into 10 power 4 exponential of, this is zero point 0.6 divided by 0.025 electron volt, and then if you solve this, then you will get 1.315 into 10 power 14 per centimeter cube. Similarly, you can calculate P in Xn at the n side of the depletion region. So this you can write P n naught exponential of Va by Kbt by Q, and that you can write 5 into 10 power 4 exponential of zero point 0.6 divided by 0.0025, and then you will get around 5.26 into 10 power 14 per centimeter cube if you solve correctly, and the answer which is matching is B option. So this was also a bit straightforward formula substitution uh, uh, problem, and this you can, so this was just straightforward. So if you have doubt, then I will be pause for some time, otherwise I'll move ahead with next question. If you have doubt, then you ask, I'll pause for some time. Okay, so let's move to let's move to next problem. Let's move to next problem. A silicon PN junction at T equals to 300 Kelvin with applied reverse bias with 5 volt has a doping concentration this and this. The built-in potential, the total potential across the junction at reverse bias of this. So this total potential in the this total is equals to VBI minus V applied, and V applied you can write as V reverse is minus 5 volt, and then you can write V total is equals to VBI plus V reverse. So this will become minus 5 volt, and this will become VBI plus 5 volt. So now you basically you need to calculate the uh, built-in voltage, so that you can calculate VBI equals to KT by Q ln NA&D by Ni square. Then if you calculate KT by Q ln, so then Na is 2 into 10 power 17 and Nd is 1 into 10 power 16. So this is 2 into 10 power 17 and it is 1 into 10 power 16 divided by this is uh, Ni square. So this will become 20. So now this will become KT by Q ln 2 multiplied by so this will become uh, so this will become 10 to the power 33 divided by 10 to the power 20, and this uh, this you can write like this. So this KT by Q ln this you can write 2 into 10 power 13. So then you can solve just like this. You can expand this log. So KT by Q ln 2 plus KT by Q ln 10 power 13. So this you can solve. So you will get around. So this is KT by Q ln 2 plus 13 times KT by Q ln 10, and this is the 60 millivolt. So this you can write 13 multiplied by 0.026, 0.06, and you can get around 0.78 something. And this factor, if you can calculate approximately, but this factor is larger compared to this, so you can get the correct answer just by this. So then basically you will get the correct answer as around point. So the correct answer will be around 0.796. So 0.796, and now the total voltage will be 0.796 plus 5 volt. So this will be 5.796 around. So this the correct answer will be 5.79. This is around 0.78, and this like approximately you can calculate just by this also. So this is the straightforward question. So if you have any confusion, then ask you can ask, or I will move ahead. So so yeah. So now the ratio of depletion with and without applied reverse bias. So basically depletion with W is directly proportional to square root of VBI minus V applied, and which will be equals to VBI plus V reverse voltage. And so depletion with applied reverse bias, but depletion with at zero bias equals to square root of, you can take ratio. So this will become VBI plus VR divided by VBI, and this if you calculate it's 5.796 divided by 0.796, which will be equals to around approximately 2.7. So the correct answer will be 2.7. This was fairly straightforward, just extension to the previous problem. So this was the one of the problem, and if you have any doubt, this was fairly straightforward problem. So let's move to next problem. A PN junction diode is subject to varying temperature and corresponding IV characteristics are plotted in figure below. Based on the given data, answer the following equation. So what will happen? So in the forward bias, change in temperature result in threshold voltage, and choose the correct option along with the region. So basically, uh, what will happen is basically your barrier. So because your VBI is directly proportional to your your the current in the forward direction is directly proportional to Ni square. So and that like the threshold voltage is dependent on the built-in voltage. As you increase the uh, increase the so this is KT by Q ln NA/ND by Ni square, and Ni square is exponential dependent on the temperature, and this Ni square leads to reduction in threshold voltage, and this factor reduces comparatively slower compared to the exponential factors. So that's why your built-in voltage reduces as you increase the temperature, and so your current will get increased. So basically, if you are operating at applied bias as suppose here, then you will get the lower threshold voltage for the temperature, higher temperature. So then this correct answer will be Ta will be greater than Tb, and uh, So, this you can account the increase in Ni, basically increase in the energy of the electrons, and the threshold voltage because of that region decreases. So let's just analyze the choices. As the temperature increase, the as the temperature increase, the scattering of charge carrier increase, and this is not the correct answer. As the temperature increase, energy of charge carrier decrease. This is wrong. Energy of charge carrier increases. As the temperature increase, energy of charge carrier increases. Hence, VT increases. This is wrong. As the temperature increase, energy of charge carrier increase. Hence, VT is increase. Therefore, TA is greater than TB. This is the correct choice. And last one, as the temperature increase, scattering of carrier decrease, and hence the VT decrease. This is wrong. So next problem, in the reverse bias that a change in temperature result in the shift in reverse saturation current. Choose the temperature along with this. So as you can see, like Js is directly proportional to Ni square. So this you can write. So the J is equals to Js time exponential of Vp V applied divided by kBt minus 1, and this J is basically Ni square divided by so Q and D. So it is a function of dP Lp Nd plus uh, Q times Tn Ln something Na. So some function is there, and this is directly proportional to Ni square. So as your temperature increase, Ni square increase, because Ni square is exponential of minus Eg by Nc Nb uh, square root divided by 2 kT. So as your temperature increase, this factor reduces and Ni square increase. So then your reverse saturation current will also increase. So this TT, so in this case, TT must be greater than the TC. So let's analyze the correct option. So this is wrong. No, this is wrong, and this is wrong because TT is greater than TC, but JS is directly proportional to Ni square. This is wrong. TT is greater than T3 as JS is directly proportional to Ni. No, this is also wrong. TT is less than TC as JS is directly proportional to Ni. This is also wrong. TT is greater than TC as JS is directly proportional to Ni square. So this is the correct answer, and last one is also wrong. So that is the correct explanation and the correct answer for this. So what is TC and TD? So basically, TC and TD, you can see this. So this hypothetical scenario, this temperature is TC. For this case, the temperature is given as so like this is lower temperature. So basically, corresponding to this curve, the temperature is TC, and corresponding to this curve, temperature is TD. So basically you need to find like how the relation is, like how why this curve will get shifted actually. So this can be either due to temperature, or you can the other case is like solar cell actually. So if you inject shine a light, that also creates similar kind of effect actually. So but in the solar cell, like this characteristics will go into this other quadrant, but the effect will be similar. There also the generation current is directly proportional to Ni square. So the similar kind of effect you will see. So did you get the so is that answer your query? Okay. So yeah. So if you have any doubt up to now, you can ask before moving to next problem. Okay, so let's move to next problem. So these were GATE 2015 question, and this is one of the time I appeared in this exam and I did wrong that time. And so the built-in potential of abrupt PN junction is 0.75 electron volt, and if it is the junction capacitance at reverse bias, uh, if it is junction capacitance Cj at reverse bias of 1.25 electron volt is 5 picofarad, the value of Cj at when reverse bias voltage is 7.25. So now, so as you can see, Cj is inversely proportional to depletion width. So depletion capacitance is you can write epsilon not A by D. Depletion you can take as a parallel plate capacitor kind of scenario, and this WD is directly proportional to square root of VBI minus V applied. And now since it's given that V applied is reverse bias, so we will take V applied as a negative. So basically, what mistake I did in my time, I took by mistake in exam pressure, I took directly proportional. So now, so basically, C at 7.25 divided by C at 1.25 will be equals to VBI plus 7.25 VBI plus 1.25 divided by VBI. No, no, just wait. Yeah. So VBI. Let me write it clearly. I am if I'm now it's confused. So okay. So this you can write uh, C at 7.5 uh, divide by C at to 1.25 is equals to 1 by square root of VBI plus 7.5 divide by 1 by square root of VBI plus 1.25, and this you can write as, so this you can take this denominator will come down and it will become square root of VBI at plus 1.25 divide by VBI plus 7.5, and then basically you can write square root of VBI is 0.75 plus 1.25 divide by 0.75 plus 7.5. So 7 point, no, this is 7.25. So now this will become uh, upper up, it will become 8, it will become 2, and down it will become, denominator will become 8, and you can calculate this by 4, and this you take square root, it will become square 2. So basically C at 7.25 will be equals to C at 1.25 multiplied by half. Now you put the value of this as 5 micron. So 5 multiplied by half, and this will become 2.5 microfarad. So the correct answer is 2.5, and so the correct answer is this one. And in my case, I choices this one at that time, so I lost 2 penalty point in that. So like this was the this year previous year practice problem set for this case. So if you have any other doubt related to the content whatever covered up to now, you can ask. I will wait for some time, and this was the content from my side. If you have any question, you can ask related to the content which I covered in the this series, or any question related to the lecture series this week, or any question related to previous this session or lecture session or any other session. I will pause for some time, and if you have question, then please raise your hand or type or whatever you feel comfortable you ask. Explanation. Okay. So basically, see like this, if you calculate this like this factor, so basically what will happen? So uh, basically this you can see basically you need to calculate like what is the built-in voltage, how it will vary actually. So let's say this Ni square. So this is a function of Ni square. So and Ni is exponentially square root of Nc Nd exponential of minus Eg by 2 kt, and Ni square will become square root of Nc will become Nc Nv times exponential of minus Eg by kt. So now, if you calculate this, as you increase the temperature, then basically, if you increase this temperature, then this term will become smaller, exponential, because this is in negative direction. So this term will become smaller, and so this term will become smaller. This term will become smaller, and this term will become larger because this is negative. So exponentially, the exponential negative function goes like this. So if you this is exponential of minus x and x. So as you go approach to a zero or negative direction, this exponential will get increase actually. So this will get ni square will get increase, and as you can see like this temperature dependence on this will be this is a function of like, and even ET also increase based on the temperature. So this factor this factor compared to this factor, the exponential factor increase is larger compared to the linear factor, and you will see a decrease in the built-in voltage. So now so that now because of that your threshold voltage also will get reduced, because threshold voltage for diode threshold voltage is like you can model as some function of some surface potential plus dBi square root of dBi, its relation it follows. So that's why your threshold voltage also get reduced actually. So then basically with increase in temperature, so this curve will have threshold voltage is at this, and this curve has a threshold voltage this. So so whichever has the a smaller threshold voltage, which has will have the larger temperature actually. So is that answer your query? Okay, fine. Yeah. So is there any doubt in other problem? Is that clear, right? So this portion is quite important. Like last few year trend is in the gate and a competitive exam. This portion kind of portion is quite important actually. You will get this depletion, capacitance, and junction. Like nowadays, days the question are becoming bit harder in gate and those exams, especially in this domain, because in general average level of like student is increasing. So that is a better trend. So yeah, so that is the okay. Any kind of reference. So you mostly follow, I think, lecture series very disciplinedly, and like if your time permit, then you can see this Donald Lehman or Benji statement. Right, that will be more than sufficient for this, and you can try solving this uh, like this practice set, like whatever I said, solve like the pattern will be similar, or you can even solve previous year gate problem also, like that also may be relevant for this course actually. So that so this mostly questions are, I think, from previous year gate questions actually. So the pattern will be similar. So that you can solve. And so is that answer your question or query as okay? So but my suggestion is like like the way to follow a book is, like especially the basic book is, don't jump too many book, like take one book and complete it actually, like follow it like very disciplinedly actually. So that is much better stand than trying to read from 10 different books actually, especially at the especially at the uh, like this kind of course at beginner levels course actually. So try to Disciplinely, you can take any book actually. So Donald Lehman or Streetman and Banerjee, or like one or more book is there, or Physics of Semiconductor by SMG. That is bit higher level text, but that also it's very detail oriented actually. And if you want more advanced treatment, then you can follow that also, like uh, uh, semiconductor devices by semiconductor devices by Robert Pierre. I think this is available on Amazon, or you can find some copy somewhere. So this is also one of the good book. But my suggestion is like use one of these books, not all actually. So you won't get time, and if you lag behind, then you won't cover much subject. So that I you follow one of this, either this PRA or solid state devices by Streetman Banerjee, uh, or solid state devices by Donald Nina. So these are the some suggested tech reference. Use only until you are pro level. Use only one at a time, not all. That mistake we used to do in our time, but you should not do those mistakes. Try to read one with complete understanding. Okay. So any other? Yeah. Hello. Yeah. Yeah. Sanjeev. Okay. Yeah. Thank you so much. Okay. You have any like some people has joined recently. So do you have any doubt related to any like you can recollect any doubt, any confusion you have? Let me try to. I will try my best to explain you better way if you have any. I will wait for some time. Yeah. Okay, then thank you so much. This was all from my end. I would like to answer any query you can you can ask, or like otherwise we will end this session and we will meet next week same time on the same platform. Till then, thank you so much and all the best for your exam. Do well and cover the content, whatever been discussed in the class, or the practice problem which are discussed here. Try to solve those problem by your own, and then possibly look for solutions. And then all the best for your exam. And I hope you will all shine with great like you will find very ease with the exams. So thank you so much. We will meet next week on the same platform at the same time. Bye. Have a nice day and nice week throughout, and happy learning. Thank you so much.